For this video, I'll be talking about an important research paper called Steps Toward Artificial Intelligence. So this is the author, Marvin Minsky. He was an American cognitive scientist and computer scientist. He was really a pioneer in the field of AI. As a researcher, he was there right at the beginning. And unfortunately, he has passed away. But he won a Turing Award in 1969, which is kind of like a Nobel Prize, but for computer scientists. So here's the paper. It was published in 1962, and it's an overview of the field of AI at that time. So basically just trying to bring together all in one document. Here's the main things that we've found so far. Before I get into the paper, I just want to remind people that this is what a computer used to look like. So no keyboard, no screen, just some dials, and it's ginormous. If you're trying to write software on it, obviously you can't type it, so you just feed it punch cards, which I'm assuming these are reams of punch cards, but I honestly don't know. So pretty barbaric system there, and it only had 16 kilobytes of memory, at least this one. This is an IBM 1401. And so 16 kilobytes, I mean, that's this picture that we're looking at is probably more than that. So I am amazed at that anything was accomplished with equipment like this. And so they'd actually accomplished quite a bit in AI. So got computers to play chess and sometimes beat human beings occasionally, prove mathematical theorems, just basic ones, but that's pretty cool, and recognize handwriting. So how does an AI find solutions? So requirement, so we need it to be easy to verify a solution. The problem needs to be well defined. So one basic strategy would be just search everything, look at all possible solutions, but that's impractical. So a game of chess, which we would consider quite trivial compared to the real world, has 10 to the 120 possible outcomes. So it's 120 zeros. There are more outcomes of chess than there are atoms in the universe. So let's not do that. Instead, you want your algorithm to find a good enough solution. So we're going to settle for not a perfect solution. And we need to take advantage of our knowledge going into this, while we're programming this. And the machine itself needs to use what it has learned while searching. So onto the topic of learning. So when faced with a new problem, a good technique is try using past techniques that work for similar problems. No problem is identical though, so you have to be able to generalize, kind of identify the important pieces. So for a human being, how do we generalize? We'll kind of construct an ideal / typical version of things. For example, a car is a general concept. We can picture a typical car in our minds, without knowing, independent of like what model it is, what color it is, blah, blah, blah. We can picture a typical version. So a machine has to be able to do something similar, but machines like numbers. So instead of sort of an ideal concept, we have we use the average or mean. So for example, what's the typical height of a human? That's a similar question to saying what's the average height of a human. So it does kind of make sense. Many averaging techniques exist for machine learning. Um, so now let's talk about reinforcement learning. This idea is definitely still in use today um, in AI. So we've got the computer and we have the environment, and the environment's emitting stimuli, and the computer has to give a response. And we want it to give a good response, not a bad response. So we have this trainer here that gives the machine feedback and tells it whether it did the right thing. And the idea is that over time, the machine can um, kind of identify the pattern of, oh, okay, this is where I made a mistake, so don't do that anymore. Oh, the trainer liked it when I did this, so keep doing that. Um, Now, one limitation of this version we're looking at here is the machine is dependent on the trainer, so the trainer kind of always has to be there. But there's other versions where, more complicated versions, where you have the machine goes through some training at first, and then later on it kind of becomes independent, and it can give feedback to itself, and it doesn't need the trainer anymore. But we need accurate feedback in order to improve. For example, if you want to be a pro basketball player, you're probably going to watch recordings of yourself playing. If you miss the shot, you try to identify what went wrong so that you can not repeat that in the future. It's kind of the same with computers, so they have to be able to grade their own performance in order to learn. But this requires it to numerically grade every decision it made, which is not always so easy to do. So, for example, suppose you win a game of chess. Well, obviously, checkmate helped you win. You can't win without checkmate, but what about, move 32 from 50 turns ago? How useful was that in helping you win? How do you assign a number that represents, how good of a move that was? And so this is the credit assignment problem. So what if that move is kind of useless on its own? What if it only is accomplishing something for like an overall, let's say 10 move strategy? So we can't just look at moves one at a time without context. We have to be able to group them together. And so Minsky says we need to structure moves hierarchically or recursively. And this credit assignment problem and feedback and stuff, it applies to many problems, not just games. So on to models. A model is a simplified representation of reality. So for example, Newtonian physics is a model. You probably learned it in high school. So it's relatively understandable, it's predictive, and importantly, it's reductive. So it includes the important parts and doesn't include a lot of irrelevant details, which makes it more understandable. Um, and it's also worth noting it's not necessarily 100% accurate to reality. Um, so, for example, you might need Einstein's physics, which is, as far as I know, somewhat incompatible with Newtonian physics, um, in order to do certain problems. However, that doesn't mean Newtonian physics is a bad model. It just doesn't apply in all cases. Um, Models are very important for artificial intelligence. Um, so here's one example of where you would need a model. So suppose a self-driving car hits someone. It should be able to explain like its decisions that led it to do that. And so if you got hit and you asked the car, why did you do that? Um, and it starts saying on line 32, x plus y plus 7, printf, blah, blah, blah. It starts spitting out a bunch of code that it ran. That's not a good explanation. Um, and likewise, if it was a human being driving the car that hit you, and that person's explanation is, well, this series of synapses fired, which went to my nervous system, and that caused my hand to move and turn the wheel, and that's how I hit you. Um, that's also a really bad explanation. So, for a good explanation, the robot or the human being, needs to have a model of itself and of the environment. So, on to some closing thoughts here. So, Minsky asks, can machines be intelligent? He says, we consider something intelligent if it did something cool and we don't understand how it did it. So he's kind of saying once we understand, we start to view it as mechanical and not intelligent. However, Minsky views this as kind of irrelevant philosophical question. So he says a complex set of algorithms might be enough to achieve intelligence. So Minsky had some predictions. So for context, in 1962, computers could not multitask. They could only execute one job at a time, but Minsky sensed that this was going to change. So he said, once computers can multitask, they will become our thinking aids. These thinking aids will perhaps for a time be dominant in our advance toward artificial intelligence. So what actually happened, 50 years later, what do things look like? So he was correct. We did get multitasking computers, and they did become our thinking aids, and a lot more. And they're still dominant today, though. So here, he makes it sound like this is an incremental step, and then we'll be at AI, but that didn't exactly happen. So, during Minsky's time, at the beginnings of AI, there was a lot of low-hanging fruit. So within a few years, they had computers proving theorems and playing chess and recognizing handwriting. So he thought that that kind of rapid progress would continue, and that AI would have been solved decades ago. So he was incorrect about that. So progress has been made, but we still don't have a true AI.